Okay, moving on to page 2. Apparently I can't enlarge this so you guys can read the question on your page, even though it's a little tiny here for me on this page, but it says a Navy ship is located 400 meters directly from a shoreline. A team of 6 Navy SEALs is to offer land support at a location 2 kilometers north of the shoreline. So I'm going to start with drawing this kind of start of the picture. So I'm going to go north and south because it says something is 2 kilometers north. It says a Navy ship is located 400 meters directly from the shoreline. So this, obviously the line I just drew was the shoreline. So I'm going to do my Navy ship out here. It's directly 400 meters, which means it's going to create that right angle right there. Directly is implying that you have that 90-degree intersection if you were to draw, this line right here. And I could even make that line dotted if I wanted to, because it doesn't really exist. It's just a line of sight. So right there. Then it says that the Navy SEALs offer land support 2 kilometers north of this point. So we want 2 kilometers north. Well, this whole thing is 2 kilometers. But if this first numerical value was in meters, then I should change my 2 kilometers into 2,000 meters. So I know this distance from there to there is 2,000 meters. Okay, then it says they are able to travel at a speed of 10 meters per second in water and a speed of 12 meters per second once on land. So all of this over here is my water, and all of this over here is my land, right? So maybe I should make that green. But I was thinking sand on a shoreline. So all of this over here is land. So at what location should these Navy SEALs come ashore if they want to minimize their arrival time? So they go a little bit slower in the water. So at some point, they're going to travel in the water. This certain point, they're going to go on land, and they're going to travel the rest of the way on land. So this is going to be kind of what they do right there in their travels. So they're going to come here, they're going to go across in the water, and then they're going to go up the land to get to this final destination. So it seems to me that we have a distance we're talking about, we have a rate, and it's asking us to find, to minimize their arrival time. So we have a distance equals rate times time problem. But if we're trying to minimize their arrival time, then we probably want to isolate our time, so because that's the one we're trying to find. So what do we have? We're trying to get a total time minimized. We have some of the time is here in the water. Hopefully you're saying to yourself. And then we're going to add that to the time that is on land. Right? So we have our total time equals the time in the water plus the time in land. Okay, well, how do we get our time in the water? We're going to have to do the distance covered in the water divided by the rate that you can go in the water. And then how do you get your time on land? Well, it's the distance covered on the land divided by the rate of when you're on the land. So the rates were given, so that's the easy part, right? So in the water, we have 10 meters per second, and in the land, we have 12 meters per second. So what we're trying to find is the distance. So we were given one distance, that the distance in this water here was 400 meters. So we know this distance is 400 meters. We know this entire distance across here is 2,000 meters. But what we're going to do is we're going to have to split that 2,000 into 2,000, and then this bit up here is going to be 2,000 minus x. Okay, well, if we want to find this numerical value here in the water, then we're going to have to use good old Pythagorean theorem. So this distance right here is going to be x squared plus 400 squared, except then you have to take the square root of that because it's the hypotenuse. So remember, a squared plus b squared equals c squared. Well, that's 400 squared plus x squared equals c squared, but then you have to take the square root. So the distance in the water is the square root of x squared plus 400 squared. And then you have your distance on land, which we just said if the whole thing is 2,000 meters, and we call this bit here in the right triangle x, then that means this leftover bit is 2000 minus x. So that's it. This is your equation that you have. It's the total time is the distance divided by rate in the water plus the distance divided by rate in the land, and we add that together. So now maybe pause, take out your calculator, graph that. I'll sketch a graph over here on the side. So your x is representing your what? Well, that's your distance, right? So my x-axis is your distance, and my y-axis is my time, because that's what my y is. We're trying to minimize our y value, our time, so we should have a dip in our curve. And when will that occur? Well, you should have found your minimum when you did that graph, and you would have seen that the x value, when you have a minimum, the x value is 603.022 meters. So the question says, at what location should they come ashore? So since this is my x, you would have to say something like, they should come ashore 603.022 meters north of point, yeah, you could put a letter there, right? Like put any kind of letter, A, B, C, whatever, north of point A. So you need to have that specific, or you could have said, 2000 minus x if you want to say that, or you'd made this x up here and this is 2000 minus x, then you could have said south of whatever and you had this point B. So you do need to be specific in your language here at the end, telling us what that point is representing or where it is. So this should be specific in saying north. They should come ashore 603.022 meters north of point A. So that's it for example 2. This is a common example. You'll see it on some, common for us. You'll see it on some previous assessments. You should go back and look at it. You'll see it in the homework. So yeah, you can go back and find it. Remember also you could check your answer. So when you get this answer, you can go back and check it, plug in the number, see if you do get the time, the total time as being a minimum, but yeah, it should be fine. Okay, moving on to example 3. Again, I can't move my paper. I don't know why. So this one I would say try on your own. I would pause right now and try the whole thing on your own and see if you can set it up. All right, so let me talk you through it. You should have gotten 1.882 feet by 5.646 feet by 4.706 feet. So I have that down here in the bottom right corner, or you can see the final answer right here up above. But it says you want to construct a box whose base length, so here's my base length, is 3 times the width, the base width. So I have x and 3x. The material used to build the top and bottom costs $10 per foot squared, and the material used to build the sides cost $6 per foot squared. The box must have a volume of 50 feet cubed, so determine the dimensions of the cost to minimize the cost. So the volume right here is our secondary equation, right? It needs to be 50. We know volume is base times height, so the base is 3x times x, which is 3x squared, times my height. I want to solve for height because I'm trying to get everything in terms of x. So height equals 50 divided by 3x squared. Then you can have your own different equation, separate equation to deal with the cost of the box. So how am I going to get the cost of the box? Well, I'm going to take the area of one of the base, and I'm going to double it because there's a top and a bottom. I'm going to take the area of the base, multiply it by 2, and I'm going to multiply it by its cost. I'm going to take the area of the front, multiply it by 2 because we have a front and a back, right? So I'm going to take the area of the front and the back, multiply it by 2, multiply it by the cost, and then I'm going to take the area of the left and right sides, right? So there's 2 sides, that's why we have 2 of them, because it's the area of a side, and then you're going to multiply it by the cost, or the price per the material, sorry. to create the cost. I apologize. So all of those you're multiplying by the prices. This is the price for the top and bottom materials, the price for the side materials, the price for the side materials, and we're multiplying that times the area. So we have some heights in there. I had to substitute in. You don't have to simplify. You just could have plugged this big equation into your calculator. When you plug it in, you graph. When you graph, you find the minimum. When you found the minimum, you should have seen the x-coordinate to be 1.882. Well, what was that x representing? It was representing a dimension, right? The dimensions of the box. What was the y representing? That was representing the cost. And so you should have seen that the dimension for x was 1.882, so that's one dimension. You triple it to get the next one, which is 5.646, and then you plug it in here to get the height, which is 4.706. So there are your dimensions, and you're done. All right.